It's about time we spoke about Vine copulas, and not just at a high level, but really getting into the detail. What are Vine copulas? Why they're useful in statistical arbitrage trading or pairs trading? And how do you build them in general? How does this all work? Because this is what I would call an advanced topic. And of course, there's plenty of research still to do in this area. And so I felt that by going through this in detail, also requested by yourselves on the channel, we can start making more progress when it comes to analyzing the relationships between different assets. So first of all, why do we care about Vine copulas? Well, right now you can see this chart. You're used to seeing this chart. There's two assets here, Pippin USDT versus Rare USDT. Whenever this chart goes deeply in the red, typically a trader might go long on Rare and short on Pippin. And when it goes high up in the blue, they might go long on Pippin and short on Rare. And so this is pairs trading. It's statistical arbitrage. It's looking at the relationship between two assets. But we can also look at the relationship between an asset and multiple other assets, not just two of them, but say three of them, four of them, five of them, six of them, if you want to, or more. And we can do that using copulas. And the way we do it is by constructing this term, the Vine copula, and you'll see why it's called that later on. Now, this was pointed out actually by a paper that I got through watching a Hudson and Thames video. I'll show you that video in a moment. But this paper really researched what was the impact of trading Vine copulas versus other strategies against the S&P 500. And you'll see that the Vine strategy here came out way on top. So this is an empirical paper here. You can see the authors that published it here at the top. I actually just got the free version from econstore.eu. This isn't the full paper, but you get the point. This is something that Hudson and Thames mentioned here in this video to say that, hey, Vine copulas have a heck of a lot of potential and is an area that we don't have the same research or level of research or volume of research as we do for other statistical arbitrage-based strategies. And so this video here by Hudson and Thames was covered by this gentleman here who did a fantastic job. And I'm hoping that by going through this video, this will prime you and get you ready to watch that Hudson and Thames video. Maybe you've seen the Hudson and Thames video. If you followed it, great. You might not need this video. If you didn't quite follow that video, if it was a bit over your head, then I think this video will be very useful for you. And of course, I'd like to give credit here to Paul Sweeting as well. He's also done a series here on Vine copulas, and this is more from like an actuary point of view. And he did an excellent job there in covering copulas. I've mentioned him before on the channel. Finally, one other resource that I found very useful was this analyzing dependent data with Vine copulas. If you hate math, if you don't want to touch math, then this book definitely won't be for you. If you don't mind the math, if you really want to go through the rigor and you're very interested in this topic, it's probably worth acquiring. When talking about copulas, we are going to be looking at the math too, but you don't have to care about the math or know the math if you just want to understand the concepts, because I'm going to be explaining the concepts and explaining how the math works as well. If learning the math is something you're interested in, then mastering this financial econometrics for time series analysis course is going to be really useful for you. This is the most recent Udemy course here where it goes over all of the concepts we've been learning here on this channel, just all bundled up in one course. So please, by all means, go through that. That will equip you with the knowledge on how to actually read the math formulas to begin with, how probability distributions work, all of that stuff. But with that said, you don't have to go through this to understand the video here. I'm going to do my best to break it down for you. Now, it wouldn't make much sense to talk about Vine copulas without first talking about copulas. What are copulas? And we've covered that before here on this channel, of course, in the course as well. But let's start from the very beginning. And let's say, what is the probability at any given snapshot in time that the last day's returns of Bitcoin and Ethereum will jointly both be up 1%? So if I looked at Bitcoin's returns, they're plus 1%, and Ethereum's returns are plus 1% or more, 1% or more. Well, I could answer that here individually. I could take the density here of Bitcoin. So this is a density curve here looking at Bitcoin. For those of you who are into the math side, that green line is just a t distribution over there. But you can see here the probability that Bitcoin lands in any given area. So around 0% is where it happens most often. But if you were looking for greater than or equal to 5%, that's going to happen 5% of the time. or greater than or equal to 1%, it's going to be 34% of the time. Ethereum's numbers are a bit higher, 39% and nearly 9%, 8.9% here, because it's a bit more volatile. So you can see here the probability of the returns of Ethereum on any given day. And by the way, I used about nearly 2,000 days worth of data to come up with all the numbers you're going to see throughout here. So this is based on quite a lot of history, quite a number of years worth of history. So you can see here Ethereum's a bit more volatile. And we can also analyze Ethereum a different way. We don't have to look at it just at any point. This is known as a point density here. We could also look at it based on a cumulative density, which is essentially just that chart before and summed up. So for example, here on the right, I could say, what is the probability of Ethereum's returns being less than or equal to 2.5% on any given day? And here we can see by following up the chart that it's about 0.2, otherwise known as about 20%. So this is known as a cumulative density function or distribution. And the chart on the left is just your typical point density function. So it's looking at, points in time, not up until. But you can see that we are summing that essentially. It's like the area under the curve of the left chart gets us to the right chart. That's basically what the cumulative means. Now, just notice quickly as well, you'll notice this word marginal. Whenever you hear marginal in the context of copulas or joint probabilities, marginal just means that asset on its own. And right now, this is just Ethereum on its own. It's not tied to Bitcoin or anything like that yet. Now, if I was to get Bitcoin and Ethereum and tie them together, I would get a joint density curve. And that looks like this. So we're going from the chart here that's on the left with this sort of green spike to this chart over here where we have Ethereum on the x-axis, Bitcoin on the y-axis, and density here on the z-axis. What's the probability of them jointly reaching these numbers? So for example, we could look here at 1% and 1%, and you'd see that if you could follow your eye sort of up the mountain, you'd see that probability is extremely high. Now, this joint density was actually put together using this formula. I'm not going to go over it in detail, but this is essentially a bivariate normal distribution. Bivariate meaning two. You can have multivariate distributions. And the limitation here is this assumes both Ethereum and Bitcoin follow a normal distribution, which we know they don't. And that's another reason copulas, as you'll find out, come in really useful. We know that these assets don't follow normal distributions. They're closer to a student T distribution, but really when we have a lot of data points, we use what's known as an empirical distribution. They have their own curve. It doesn't follow the normal distribution. Now, to make this joint density easier to sort of see and tell what's going on, we can look at it from a bird's eye point of view. So this is a top-down view of that joint density. So here, for example, if I was to follow up with 1% on Bitcoin on the bottom and 1% with Ethereum, you'll see here that it's really close to the bright yellow, meaning the density, the probability of those two things happening at any given point in time are really high. Because they do move alike. Bitcoin and Ethereum are positively correlated. Number one, you can actually tell that. Conversely, if I was to say plus 5% for Bitcoin and plus 5% for Ethereum, it's not impossible or improbable. It does happen, but that probability starts to go down the mountain, right? It goes down the slope. That probability is a bit lower, as we've seen before on their marginal densities as well. Now, if I was to say, what's the probability of Bitcoin being up 5% and Ethereum being negative 5% here, it would say that's very improbable. That's almost never happening. Now, just like before, where we had a cumulative density function, here we can do the same with our 3D chart. So if you were to take on the left here our point density joint function, and turn that into cumulative, you'll see we get this, the mountain essentially becomes a slope, just like the 2D version, but now it's in 3D. And we can look at that over here to say, what is the probability of Bitcoin being less than or equal to 5% and Ethereum being less than or equal to 5%? And you'll see that probability is 88.3%, which makes sense. It makes sense because, and I say 88.3 here, by the way, I calculated that. If you were just looking at the color, you wouldn't be able to tell that. But I say it makes sense because we know that on any given day, it's likely to be around 0 and 5% isn't that far-fetched. So for it to be less than or equal to 5% on both sides is at the same time is a really, really high chance. But guess what we can do, right? We can take this density here and we can actually break it down into further components. We can actually break it down into its marginal densities. So you can see the middle and the bottom right here, we have these two density functions here, point density functions for Ethereum and Bitcoin. And if we understand the dependency between them, the relationship between them, which is actually the chart on the very left, we can get to our joint density function, which is our mountain on the top. So that mountain on the top can be broken down by these three charts. What do I mean by that? What is this chart on the very left? That chart on the very left is a copula, and a copula describes the probability of these two assets moving alike given their returns are in a certain range. So for example, here, if Bitcoin's returns were really high and Ethereum's returns are very high, then it's very likely that they're going to move alike, right? That you see this massive spike up. Conversely, if they're very low, then you see a spike up on the other end. And it's really the stingray looking pattern here. We're going to go into it in a lot more detail. So don't worry if that's gone a bit over your head. But what this math function here is saying is it's saying, hey, the function of x1 and x2, i.e. Bitcoin and Ethereum in our case, can be made up of this copula, which is essentially the relationship here between these two assets, their dependency, multiplied by their individual 2D distributions that we looked at earlier, whether you're using a student t or elliptical or Gaussian, normal, whatever it is you're using. You can actually compose a joint distribution now based on those. And you can do it using this idea of a copula. And a copula is just describing how these two assets behave together. It's separating out from their marginal distributions their actual relationship, which is really, really interesting. Just for those of you who are interested in the math, here we can actually replace this f1, x1, and f2, x2, which is saying they each have their own individual density functions, and we can replace that here with u1 and u2. In other words, all we need to do is fit Ethereum to its whatever distribution you want to use, student t, empirical, whatever it is you want to use, and that will give you a value between 0 and 1, as we saw before. You look on the x-axis and you follow along to the left, and then you get a number between 0 and 1. So as long as you can scale Ethereum between 0 and 1 and Bitcoin between 0 and 1, you can fit this copula. And by the way, this is all fitting within something known as Sklar's theorem. We know we can do this because of something known as Sklar's theorem. And you can learn about that with some of the other resources that I've given you or some of the prior videos on this channel as well. But the good news is we can essentially make this math look a bit more simple by employing here this cumulative density function to change or convert. And this is known as a probability integral transform. But we can convert our minus infinity percent, whatever. It goes from minus infinity to plus infinity, whatever our percentage is. We can convert it and squash it between 0 and 1. And when we do that, our math formula looks a lot more simple. Instead of the f1, x1, f2, x2, etc., we now just have u1 and u2. And that just means Bitcoin and Ethereum scaled between 0 and 1. And actually, when you look here at the copula density on the bottom left, you can see that the scaling on the x and y axis is between 0 and 1. And now you know why. Now, the interesting thing is, when you look at the bivariate joint distribution, or density, I should say, that we looked at before, so that mountain, you can see in this formula, there's this rho symbol. It looks like a P, but it actually means rho. It means correlation. And this is here looking at a Gaussian copula on the bottom left as well. In other words, like a normal distribution, but for copulas. And this here is describing, in this function, this is describing the dependency between x and y, or x1 and x2. Here it's x and y in the formula, but we're calling it x1 and x2. That row is describing it. It's describing their relationship, meaning we can see that we have our marginals, our x and our y, or our x1 and our x2, however you want to call it. And we have another term, which is this correlation. Correlation is a dependency metric. All we're doing here is putting that on steroids. We're breaking that down into its own probability density function. For example, let's say you care about risk, right? You want to manage your risk in a portfolio. You might care if certain assets tend to follow each other more in extreme downturns, because that means your portfolio is less diversified. And in that case, you might want to change up your portfolio, change the mix of assets you've got that aren't correlated in extreme downturns. So that's just one reason an actuary, for example, might be interested in, or a portfolio manager, I should say, might be interested in copulas, because it can actually describe how that dependency strengthens in extreme movements to the up or to the down. And so here, when we look at this copula over here, now we can see it a bit better because it's bigger on the screen. You can see the spikes I was talking about in the two corners there, but it's easier to see if we flatten this again to 2 dimensions and look at it from a bird's eye view. We can see that on the far left and the far right and upper of the chart, that the chances of these two assets moving together in extreme downturns or upturns is far higher. Now, I say that with a caveat, by the way. This is assuming they follow a Gaussian density and there are different types of copulas that we can model. Just like a normal distribution doesn't fit Bitcoin very well, a normal copula density, i.e. a Gaussian copula density, might not be the best fit for Bitcoin and Ethereum. And in fact, as of today, it's really not. So we can see, for example, that this Gaussian copula density might not be the best fit. So what actually is, and it is this Clayton copula density, which looks a bit different. In fact, the Clayton copula looks like this. It looks more like a stingray. It's got this big pointy tail here, and then it sort of folds up towards the upper right. And if we look at this from a top-down view, what this is saying is when these two assets move to the extreme downside, and by the way, this is assuming we're talking about returns here. It's actually their prices, I should say, when I modeled Bitcoin and Ethereum, where they follow a Clayton copula. But let's just pretend it's returns for now. I'll come on to that later on. But here you can see we have this Clayton copula over here. What this says is there's still dependency between them as prices move to, or returns, I should say, move to an extreme upside, but not nearly as strong as when they're moving to extreme downside. So when the market's tanking, Bitcoin and Ethereum are going to move a lot more alike. They're going to have the same days that are up, the same days that are down. They're going to match like for like. But when prices start rising a lot, then they tend to try to do their own thing a little bit more. And you probably, if you've been trading in the markets, you would have seen that firsthand. You wouldn't need a copula to tell you that. So for example, the chances of Bitcoin here being really, really high, here it's at 0.8. And remember, everything's now scaled between 0 and 1. So that 0.8 could mean a return of, 11% for Bitcoin. Or if this is based on prices, it could be a price of $100,000 for a Bitcoin. And Ethereum is here at 0.4, so 0.8 versus 0.4. That probability is quite unlikely. Now, let me show you something really, really interesting, because here's a real snapshot taken from Crypto Wizards of Bitcoin and Ethereum's prices here. And you can see that their prices do, in fact, follow this Clayton pattern. You can see that the dependency strengthens a lot as prices go to extreme lows. But as they move to higher highs, then we get this more of a fan out, this sort of stingray fold sort of flapping up a bit. So this is a snapshot taken from the past pretty much. And you can see here that Bitcoin's price was really, really high, but Ethereum's was remaining really, really low. And this is what it looks like today. You can see now the relation between the two is more within the boundaries of this Clayton copula. So before we were low down here and now we're up there. And in fact, on Twitter, I don't tweet much at all, but occasionally I do reply to posts on Twitter. And Ash Crypto had posted, this whole thing about Ethereum, what's wrong with Ethereum, buy Bitcoin, Bitcoin's doing better. And I kept posting the screenshot saying, guys, like, short Bitcoin, long Ethereum, market neutral strategy. Here's where they are over the last 2,000 days. Like Ethereum is going to rise versus Bitcoin. Make no mistake. Now, I'm not here to give anyone advice on how to trade, but to me, it was so obvious. I wanted people to have the data. And so now you can see that yourself. So it's gone from there. Now today it's over here. It's more within the band. So the trade isn't as obvious anymore. But this is an example of how copulas were used and are used at Crypto Wizard. You can put in any pair you want today, and you'll see where they are on this chart, and also what sort of copula relationship best fits them within the Gaussian, the student T, the Clayton, and the Gumbel copula. Those are the four that we look at today. But if I overlay the copula on top of that data, you can see kind of what I'm talking about there, hopefully. And so here's where it is today. The probability of Bitcoin given Ethereum, or Bitcoin being less than or equal to where it is given where Ethereum's price is 99.1%. It's like, yeah, it's super likely because Bitcoin's price relative to Ethereum right now is really high. However, Ethereum's price being less than or equal to where it is given where Bitcoin's price is today is just 8.9%. And that looks something like this. So Bitcoin, when I put this together, by the way, Bitcoin was at $104,000, Ethereum at 2.5K. The way we'd write this mathematically is the probability of Bitcoin being less than or equal to 104, given Ethereum's at 2.5K, is really, really, really high, because that's a really high price for Bitcoin to be at. Conversely, if Ethereum's less than or equal to 2.5K, given where Bitcoin is, it's 8.9%. Now, if that was under 5% and the formula on the left was over 95%, we could say that there's a pairs trade there. And when they both normalize to around 50%, for example, you could close that trade. And that's how to do statistical arbitrage with just normal copulas. Again, this is all over Crypto Wizards. Like, you can see these charts everywhere. So in order to make this work, we have step one, which is fit your distributions to your assets, whether you use empirical, in other words, the actual distribution that they formulated, or a student T distribution, something like that. That's step one, because you need to do the probability integral transform, where you are transforming the value, whatever that value is. It could be any number. If you're looking at the returns, for example, or the price, it could be any number, but you need to squeeze that between 0 and 1. Then in step two, we fit a copula to those and we determine which copula fits best. Here I was using prices, for example, and I found that the Clayton copula actually works best. Now, actually looking at this today, you can see it's at 98.6% and 9.2%. Over there, but I can also flip this here to say returns. And you'll see here when I do that it actually follows a student T copula. So when we're looking at the returns, not the prices, it follows a different pattern over here. So for example, if that red dot was way up there, it would suggest that at that specific point in time, and you wouldn't just go short on Ethereum and long on Bitcoin if that happened, by the way, because when you're dealing with returns, you actually need to look at them cumulatively. But over here, when we're looking at prices, it kind of does that, right? So this is one way to do it. When we look at Vine copulas, we're going to do it based on returns, and I'll talk about, that cumulative approach. Now, that has been the step there for Ethereum, given Bitcoin, for example, or these two assets. But now, what if I want to add more assets in? How would I do this if I want to compare Ethereum to Bitcoin, to Solana, and to SWI, for example? One thing we could do is potentially fit these to a normal density curve and just add in X, Y, Z, or X1, X2, X3, X4. But that's probably not going to work, because remember, Ethereum might follow, say, a Gaussian, which it doesn't, by the way, might follow a Gaussian distribution. Bitcoin and Solana maybe student T, and SWI some other, maybe empirical, whatever. The point is that they're all going to follow their own student T distributions and density functions and whatever it's going to be. And also, the relationship between them might not just be a normal relationship. It might not be a Gaussian copula or Pearson's correlation coefficient that explains the relationship between all of them either. So we might have that Ethereum and Bitcoin follow the Clayton copula on their returns, which we know, by the way, they don't actually follow a student T right now. But then the Gaussian might be the best for Bitcoin and Solana, or a Gumbel for SWI and Solana, whatever those relationships are. There might be better relationships here that we can describe between these different cryptos that follow different copulas. And so we're now left with this issue of, I want to understand, where is Ethereum versus these other cryptos? Is there an opportunity to potentially trade over here? But I can't, because I don't have a math formula that kind of perfectly describes them and shows me that there's an opportunity. And that here is really part two here, where we talk about Vine copulas. You see, Vine copulas will be able to take something like this and say, well, let's just throw that out the box because we can't do that. And what Vine copulas will do, we'll say, let's just break them down between their separate relationships. Let's look at Ethereum versus Bitcoin. Let's look at Solana versus Sui. Let's look at Solana versus Bitcoin. Let's look at Solana versus Ethereum. Let's look at Bitcoin versus Sui. Let's look at Ethereum versus Sui. And let's build our own probability density function from those. So we can take any cryptos we want, and as long as we can model their bivariate copulas, we can actually get to this end result. Because remember the slide I showed earlier, this is just made up of the relationship between the cryptos, or the relationship between whatever it is you're analyzing, and their marginal density functions. So we can actually go and do that. And so the math of that would look more like this, because we've got 4 assets here. So we can look at the bivariate copulas for all of these. We can model all of these independently and get to our answer. And in fact, let's just do this with three assets. Here we have Ethereum, we have Solana, we have Bitcoin, and we can now model the 3, I should say, dimensional. It'd actually be a 4D chart if we were to do it, which I'm not sure how you would do. So I can't actually show you a chart, because now we're getting into math, which is now at another level. But we can model that like this. We take the marginal here density functions, which is f1 of x1, f2 of x2, f3 of x3. That's essentially saying, the student t of Ethereum, the Gaussian of Bitcoin, and the student t of Solana, for example, could be anything. Multiply those by what's known as the unconditional copulas here, and then multiply that by the conditional copula. And I'm going to get into that in a lot more detail. So don't worry if this has thrown you off a bit over here. We're about to get into a lot more detail, but the key thing to realize is that we can actually build our function here just by knowing what the copulas are and the relationships between these assets. Now notice in here, I have this h function over here, this h1 given 3, for example, and h2 given 3. And this is very interesting, because what this is actually saying is, what is the probability of our first asset, which could be, say, Ethereum, being less than or equal to a certain value, given our U3 asset, which, let's say Solana, is equal to some value. And of course, there's another h function as well, which says, what is the probability of our U2 asset, which is Bitcoin now, or it's the only one left. So let's pretend it's Bitcoin. Bitcoin is less than or equal to some value, given Solana, again, is equal to some value. So that's all these h functions are representing. It's actually a math formula. You get it from within the copulas. There's a way to calculate and mathematically build these functions from the copula. A lot of them are pre-done for us already, because smart mathematicians have done it, just like you'd see a normal distribution in the formula for that, right? So a lot of these actually exist, but we can actually put these together. So we can take the output of those 2 probabilities there, those h functions, and we can therefore get the probability of Ethereum being less than or equal to where it is, given Bitcoin and given where Solana is. And that is essentially how, from a trading perspective, you might become interested in Vine copulas, because when you get to that end result, it's basically telling you, is Ethereum undervalued, yes or no, in respect to the other assets. That's what that formula is telling you. And that really is the real key over here. So how would you go and actually build something like this? Well, first of all, let's look here at our relationship. We have Ethereum, Solana, and Bitcoin. So let's say that those are just connected like this. Ethereum is connected to Solana, and Bitcoin is connected to Solana as well. So what I'm going to do is replace Ethereum, Solana, and Bitcoin here with actual numbers. So 1, 3, and 2. And we'll call these our nodes, and they are connected with edges. So the lines connecting them we call an edge. So you can never have the same amount of edges as nodes or more, right? You're always going to have less edges than you are nodes. So our nodes here on the first level represent our marginal densities, the f1 of x1, f2 of x2, f3 of x3. And because it's lowercase f, we know it's the point density, not the cumulative distribution or the cumulative density, right? It's the point density. And so we can now connect to the relationships of those nodes here in tree 2. We'll call these the unconditional copulas. And you'll see here I've got a 1, 3 and a 2, 3. Because this is saying fit a copula here based on the marginals f1 of x1 and f3 of x3. So that's 1 and 3. And you can see that written in the math formula as well. The copula with the subscript 1, 3. Now, subscripts, by the way, if you do care about the math side, this doesn't mean you need to do anything with those numbers. It's giving that copula a definition. Whenever you see this sort of subscript here, C, and then lower below that C, 1 and 3, that's just saying it's its own copula. It's different to the C with 2 and 3. It's a different copula being fit differently to the other one, right? So it's a way to identify symbols being different in any kind of equation. So we're going to call it 1 and 3 because it's basically formulating the relationship here between our node 1 and 3, which is, I think, Ethereum and Solana. And so here we're fitting that copula of 1 and 3 and also 2 and 3 there. And then finally we get to the final step, which is to again fit another copula to the relationship of the relationships, right? So we can again join those two together and we can say, okay, now I need to fit a copula which is going to be 1 to given 3. So given that we know 3, we factored 3 already, it's included in these other copulas, we can now go and plug in for 1 and 2 as well. And so when we do that, we actually get our full formula here at the top. And that's how we construct a multivariate probability density from just analyzing 2 assets at a time. So we do it in this tree-like pattern. And now you can see why these are called vine copulas. We've essentially constructed this vine. Now, you've probably got tons of questions by now. Hopefully you're really lost because I can just tell you I've spent months and months on vine copulas. Like it wasn't an overnight thing for me to understand vine copulas. I found it quite challenging because different books and material, talk about the math differently. And then, to make sense of it all, you really have to have a strong grasp on probability theory. But hopefully I'm going to answer some of your questions now because our first level is essentially this F1, X1, F2, X2, F3, X3. And capital F, which is the cumulative density function, so the distribution function, there is our U1. Do you remember that's U1 actually represents squashing between 0 and 1. U2 represents squashing the other asset, which I think is Bitcoin between 0 and 1, and U3, which is Solana, squashing Solana between 0 and 1. And then we're taking all of that and we're multiplying it by the next step, which is where we're fitting our copulas. We're taking that U1 and U3 and fitting it to a copula. And we're going to call that copula C1 of 3, C sub 1, 3. So we're just giving that copula a name. It's called sub 1, 3. And then we're taking U2 and U3 and we're fitting that. So in other words, we're taking Bitcoin and Solana and fitting it to its own copula. The H functions that you can see beneath here in a sort of darker gray, these are what you get from the copula. Once you've fitted a copula, you can calculate the conditional probability. So the first one, which we'll just call V1, which is H sub 1 given 3. So we're giving that H function a name. That's where we put U1 and U3 into the H function. And here you'll see it's got this semicolon theta 1, 3. That means we're taking the parameters for that function that we got from fitting our C1, 3 copula. That's what the math is really saying there. And that gives us the probability of U1 being less than or equal to U1 given U3 is a certain value. And the same thing with V2, right? It's giving us the same thing. It's saying what is the probability of U2 being less than or equal to U2 given U3. And once we have those, we can take V1 and V2 and we can fit a new copula with V1 and V2. We'll call that C1, 2 given 3. I'll show you how we come up with these 1, 2 given 3s, 1, 3s, all of that. We're going to go through an extensive exercise on this because, again, I want to save you from a lot of headaches by giving you some headaches. So let's go through the headaches. So you have the C sub 1, 2 given 3, right? So you're going to take the V1 and V2. You're going to fit another copula based on those H functions. And that we're going to call HC. This is going to be our final copula. So the copula that gets us to the probability of U1 being less than or equal to U1 given U2 and U3 are equal to their respective values. So in other words, if U1 was a really, really low number, like 1%, right? That's going to suggest that, whoa, there's a 1% probability it is where it is. It's probably way undervalued compared to the other two when taking into account the historical data, right? So that's always the assumption. Just because that these assets have behaved a certain way in the past. Doesn't mean they always will. And that's where the risk in statistical arbitrage always is. You just need to build this so that statistically you're more right more often than not, and you build your portfolio based on that. So these H functions represent the probabilities that I've highlighted over here, and the copulas are what you need to fit in order to get the parameters for the H function. And the H function actually is derived from the copula math itself. So whenever you get, say, a Frank copula, you should get the copula formula or the copula density formula, for example, but you should also get the H function too, because you'll need both. And that is a Vine copula. So we've taken 3 assets in this example to construct a Vine copula. But what if you had something like 6 assets over here? And by the way, now I'm stealing from this book here, the Analyzing Dependent Data with Vine Copulas. So, this isn't an exact version of this book, but I've taken from a certain page in this book something to get it quite close, because I thought the example was really, really good. So let's say here that we have these 6 cryptos over here, and I identify using something known as Prim's algorithm, because another question you might have is, how do I know which connections make sense? Like, what crypto should be connected to what? Where do the relationships lie? Well, Prim's algorithm uses something known as Kendall's tau. Kendall's tau is, I'm just going to say, it's a better way to judge dependency than Pearson's correlation coefficient. Okay, so for what we're doing here, it's a better way to do it, because Pearson's correlation coefficient assumes everything is basically following a normal distribution, which we know it doesn't. So Kendall's tau is used to basically rank and organize the way assets connect together, or whatever it is you're analyzing connects together. And this sort of shape, by the way, where you have sort of a connection coming off another connection with its own connections happening on it, this is known as a regular Vine copula. So we'll call that an R vine. If it looked just like this, it's called a canonical vine, so a C vine. And if it looks like, I don't know, just a road, right? It could just be a string of these assets joined together like that. That's known as a drawable vine, or D vine. But we're going to stick, for our example here, with the regular Vine copula. And this is probably something that you might come across more often than not. I don't know. It depends on the data, how many of them you're trying to analyze at once. And I'm going to be very ambitious here in this video, because rather than analyzing 3 of these assets like we just did, rather than analyzing then 4, I'm just going to jump straight ahead to 5. Because what you'll find when you're researching Vine copulas is you'll get to 4 and you'll be like, how would it work then if I got to 5? So let's just understand 5, because if you can do 5, then you can do 4. You're probably not going to do more than 5. You'll probably actually end up doing 4. I think the paper I referenced earlier did 4. Can't remember. But anyway, we've got 5 over here we're going to analyze. And just as before, we're not going to refer to them as their crypto names. We're going to refer to them as numbers. So 1, 3, 4, 2, and 5. So you can see 1, 2, 3, and 5. They're basically a C vine, if I was to ignore 4. But all of these together are an R vine, because 4 is then connected to 3. And again, this sort of pattern here, I've adapted it slightly, but again, I'm getting this from Analyzing Dependent Data with Vine copulas. Of course, I'm not sponsored to promote this book. So now what do, right? We have our nodes. We also have our edges connecting the nodes. So we know that the edges represent the relationships, in other words, the copulas. So our edges here are going to be a copula fitting 1 and 3, 3 and 4, 1 and 5, and 1 and 2. Now, the key thing here is when we have the 1 and 3, 3 and 4, 1 and 5, 1 and 2, these copulas, we now need to figure out what are the relationships between those copulas. So we need a new tree. And so we can actually show that like this. We have 1 and 2 as a node, 1 and 3 is a node, 3 and 4 is a node, and 1 and 5 is a node. And I know how they connected because I can sort of follow from looking at the top left how those were connected before. So let's just now show new connections for those. So the next copula I'm going to need is a copula for 2 and 3, given that we have 1 modeled. Now, what do I mean by that? And how do I know what order to put all these numbers in? Like before, for example, this was obvious. I just looked at 1 and 3 and put 1 and 3, and then 3 and 4, put 3 and 4, 1 and 2, 1 and 5. Excellent. That was really straightforward. But over here, I've now got the semicolon and everything looks really weird. This is really important to understand. The connection between these, the way you do it is after the semicolon, just look for the numbers where there's more than one of them. So there's 2 of 1. So 1 goes to the right-hand side. It goes to the right-hand side of the semicolon. And then it's going to be 2, 3, because that's all that's left. So it's 2 and 3, given that we have 1. And then between 1 and 3 and 4, we can see that 3 is the common number there. So put that to the right of the semicolon. And now we have 1, 4. And between 1, 3 and 1, 5, we can see that 1 again is the common factor. So here we'll put 3, 5. Great. Now we have copulas to fit there based on those numbers. And I'm going to show you again in the math what that actually looks like. But bear with me here. Right now, just write the numbers down, because if you do this exercise, it's going to make the math part a lot easier. And I wish this was the first thing I learned, because honestly, I was like reading so much stuff. I was going over so much stuff, trying to figure out, how am I getting the numbers wrong? Why are things not coming out the way I expect, etc. And then I worked out this exercise is really handy, and it came from the book on analyzing dependent data with Vine copulas. Brilliant. Okay, so now we have our nodes on our second tree there for 2, 3 given 1, 1, 4 given 3, and 3, 5 given 1, which we just did. But now we need the relationship between those relationships. In other words, the copula between those copulas, the copula that ties those copulas together. Because remember, it's a vine structure we're trying to build here. And we've got 5 assets, not just 3. With 3 assets, it was easy. We just had one set of conditional copulas. Here we've got multiple sets of conditional copulas. When I say conditional, it's something given something else. That's conditional probability. So here we have 2, 3 given 1 and 1, 4 given 3. So we know 1 and 3 are both on the right-hand side of semicolons. So we'll put both of those on the right-hand side. And that just leaves 2 and 4. So that's then 2 and 4 given 1 and 3. And then for the other one, we have 1, 4 given 3 and 3, 5 given 1. We can see the 3 and the 1 again need to go to the right-hand side. So we do that. And then we're left with 4 and 5 given 1 and 3. And so now we have those copulas. And guess what we have to do one more time until we get down to one copula? We now need to tie those together and work out their relationship. So the final step will be to say, okay, we know 1 and 3 have to go to the right-hand side of the semicolon. We can also see that 4 occurs twice on the left-hand side of both of those. So 4 will also need to go to the right-hand side of the semicolon. The only then extra ones are 2 and 5. So that 2, 5 given 1, 3, and 4. So there we go. There's the final copula that will fit. And that completes our trees over here. So we have tree 1, tree 2, tree 3, and tree 4. I haven't drawn them like boxes like we did before, because here I'm focusing on how to actually get the numbers for the relationships. From there, we can actually construct our multivariate probability density for 5 assets. Right? I can't draw a chart for what that looks like, right? Because now we're past 4 dimensions, but I can write it mathematically. And so we can see that we have number 1, our tree 1, which is 1, 3, 4, 2, and 5. Those there are our marginal densities. And here it's not U1, U2, U3, U4, U5. I'm just showing you how to construct the multivariate density function. I'm showing you how to construct it. For trading, I actually don't need to construct it. I'm just showing you that the math here works. Now, the second level here is going to be tree 2. So here we'll have copula 1, 2, copula 1, 3, copula 3, 4, and copula 1, 5. You can see it's color-coded so that you can see exactly where those numbers came from there. Now we need U1 and U2 because you can't fit a copula without those numbers being scaled uniformly scaled between 0 and 1. Which we did by taking x1, x2, x3, x4, x5, and figuring out what probability densities and probability distribution functions, cumulative density functions, fitted them best. And so now that we have those copulas, we can multiply them all together, which we don't need to do, by the way, because we're not actually going to build this. We just need to get to the end h function for trading, by the way, just in case you're wondering. But I'm just showing you how you would build this again, just to reiterate that. So the next level are the relationships of those copulas. So another copula to describe the relationships between the copulas before. So these are now conditional copulas. The ones up here, these are unconditional because they're not conditioned on anything. Here they become conditional. And so we're taking the h function from C1 and 2, but I've reordered it because here it's got to be h2 given 1. And we know it's given 1 because that copula is 2 and 3 given 1. So here I'm just reordering the math notation a bit. This is if you're super into the math, by the way. If you're not super into the math, don't worry about paying attention to this too much. Just notice that I've reordered 2 given 1 because it's given 1 that we're trying to get to here. So we have our h function, and the parameters of that h function, by the way, are based on the copula C12. I haven't written that in here to save space, but those parameters that you're going to be using, they come from the C12 copula. The h31 function here comes from the C13 copula. The h13 again from the C13, and the h43 from the C34, and finally h31 again, and then h51 from the C15. How did I know that those are the copulas we needed? Well, just look at the red above in tree 2. So that's how we did that there. And then here, we're going to fit our 2 and 4 and our 1 and 3 over here. So that's giving us here our tree 2. Now, to get to tree 3, we need our C24 given 1, 3 and C45 given 1, 3, which again, you've got up there in green. So you know what we're doing. And now we're putting the output of our h functions before into the new h functions that come from the C23 given 1. So now, once we fitted those red copulas, so the C23 given 1, C14 given 3, C35 given 1, we're then taking the h function outputs of those and putting them into fitting a new copula for C24 given 1, 3. And finally, we just do the same thing again in the final step. And that is how we get to our final h function, which gives us the probability, in this case, for example, of u2 being less than or equal to u2, given u1 where it is u3, u4, u5, or even, for example, u5 being less than or equal to where it is. And if you wanted, for example, a different target asset, you didn't want u2 or u5, maybe you wanted something else, then again, we're actually then looking at a slightly different structure or math for all of this. But I don't want to get too complex here, and I don't want to go far into the math. This video is already complex enough. I've gone through this a lot. I've put this slide together, for example, and even looking at this now, it's so confusing. Vine copulas are actually really simple in what they're doing. They're just connecting copulas to copulas to copulas based on those h functions. You need to be careful around the ordering of what assets you're putting into those h functions, and that's why the math can actually become quite important, because it gives you the rules to follow. But the essence of what it's doing is really simple. It's complex because it's a lot to look at. The more assets you're adding, the more complexity you're adding as well. For example, if you're just looking at 4 assets, there's like 6 different ways you can rearrange those assets. And this number goes up like exponentially once you keep adding assets. The number of ways you can combine all of these to find the perfect relationship goes up, and therefore so does the compute. Once you've got these probabilities, all you need to do is subtract 0.5 from them, run them for the entire data set, so get these probabilities from the very dawn of time till today, and then cumulatively sum them. So you get this probability, you subtract 0.5, that gives you what's known as the MPI, and then you cumulatively sum them to get the CMPI. And when you do that, you end up with a chart that might look something like this. Now, I don't think these were the exact assets I used for this chart, by the way. This is just here as an example of what you might get out. But when you look at this, you say, I'm not sure I want to trade that. I mean, let's say this is here Bitcoin in relation to Chainlink and Ethereum and Solana. You might say, okay, well, when Bitcoin's at plus 1.5 or plus 2 and negative 1.5, I'll either go short or long on it, and then do the opposite with the other assets. And in fact, that brings me to a good point. I think the authors of the paper before, they weren't just going to go long on one asset and short on all the others, for example, because they might as well just short the market to be market neutral. So they would say go long on the stock and short on the S&P 500. And that's, I think, what actually led to those returns. So here, for example, you might choose to, if this was a different asset, which we'll come into in a minute, then you might go long on that one asset and then short Bitcoin, or short something that resembles the crypto market or an index for the crypto market in general. But nonetheless, here you have this chart. Now we can compare this chart to another one. Here's Chainlink as the U asset, so the probability of Chainlink being less than or equal to where it is given all the other assets. That's what this chart represents. And again, I can't remember if these were the exact assets I used for this chart, but it gives you an idea. And you can see I'd much rather trade this chart than this one. This one for me, it zigzags a lot more. For you, you might disagree, and that's fine. And actually, I think, again, what they used in the paper were Bollinger Bands for trading these. But this is much nicer to trade. It's nice and oscillating. You could use a z-score, rolling z-score. This is the full z-score I've got up here, but you could do a rolling z-score, Bollinger Bands. You could just set thresholds and trade it vanilla however you want. But the interesting thing here is if you were to run, say, an augmented Dickey-Fuller test on this versus this, I'm willing to bet money that this will come out as being more stationary. Remember, stationary, very, very, very loosely speaking, is really just saying, does it zigzag and oscillate up and down, keeping a constant mean variance and auto covariance, depending on, irrespective of where you sample. That's really what stationary means. We covered stationarity in a lot of detail in the prior series. But in other words, is this something I want to trade? And so what you can do is come up with all the relationships and all of the charts, then run the augmented Dickey-Fuller test on all of them, and that will tell you which one might be more preferable for trading. And again, I'm stealing all of this from the paper, the other videos, etc. But this gives you the general idea. So this has been your introduction to Vine copulas. I know it's a lot. I know it's heavy, but I hope that it answers some of the questions you might have had when you're looking at material elsewhere, and how to actually construct these, why they're called Vine copulas, what the math of it actually looks like, and what's the point of them in the first place, particularly from a trading point of view. Until the next one, take care and talk soon.